2818 Apply operations to maximize score. This Java code returns the maximum possible score after applying at most k operations. Explanation 1. Prime score calculation. Calculate prime score sieve static block. A static array prime scores is used to store the prime score, number of distinct prime factors, for all numbers up to max_val 100,001, slightly more than the max possible value in nums. A static initializer block runs once when the class is loaded. It calls calculate prime score sieve. The sieve works by iterating from p equals 2 up to max_val. If p is prime, initially marked true or not marked false by a smaller prime, iterate through all its multiples I equals p, 2p, 3p, up to max_val. For each multiple I, increment prime scores I. Because p is a distinct prime factor of I, we also mark multiples as not prime, is prime I equals false as a standard sieve of Eratosthenes optimization, though it's only strictly needed here to identify the primes. Page 2. Maximum score method. Get prime scores for nums, creates an array PS to hold the precomputed prime scores corresponding to the elements in the input nums list. Monotonic stack for boundaries. Right boundary, right array. Calculates right I, the index of the next greater element based on prime score. It finds the smallest index j greater than I such that psj greater than psi. If no such j exists, right I remains n. This is done by iterating from right to left. Elements with smaller or equal prime scores are popped from the stack because they cannot be the NGE for the current I, left boundary, left array. Calculates left I, the index of the previous greater or equal element based on prime score. It finds the largest index j less than I such that psj greater than equals psi. This is crucial because if psj equals psi, the element at the smaller index j wins the tiebreak and thus acts as a boundary for I. If no such j exists, left I remains -1. This is done iterating from left to right. Elements with strictly smaller prime scores are popped because they don't form a boundary. Calculate contributions array. For each index I, the number of subarrays LR, where nums I would be chosen is calculated. The valid start indices L range from left I plus 1 to I. The number of choices is I, left I. The valid end indices R range from I to right I 1. The number of choices is right I. The total number of subarrays for which nums I is the chosen element is I, left I, right I. This is stored in contributions I. Long is used to prevent potential overflow. Sort by value. An array indices is created. 0, 1, and 1. This array is sorted based on the values in nums in descending order. This ensures we prioritize multiplying by larger numbers first. Greedy calculation. Initialize final score equals 1 as a long and remaining k equals k. Iterate through the indices array, which is sorted by nums value. For the current index, get the number num equals nums.get index and its contribution count equals contributions index. Determine how many times we can apply the operation using this num. ObftoTake equals math.min remaining k, count. If obftoTake greater than 0, calculate power num, obftoTake, using the fast modular exponentiation function. Multiply the final score by this result, taking the modulo mod. Decrease remaining k by obftoTake. If remaining k becomes 0, break the loop as we've performed the maximum allowed operations. Return result, return the final score cast back to an int 3. Fast exponentiation power method. Implements the standard binary exponentiation algorithm to calculate base_express %mod efficiently, preventing overflow and reducing time complexity from O express to O log express. Thanks for watching, and I post daily.